will be a critical review on the cosmological simulations of structure formation.
Thanks very much. So it's really a great pleasure for me to be here and to tell you a little bit about the research I have been doing over the last 5 to 10 years. And in this talk, I would really initially like to tell you a little bit about what the cosmological simulations are, why we think they are a useful tool to use, and I want to then move on and to tell you about the current issues in cosmological simulations and what are the new ways forward trying to treat this issue and to make progress in the field. So I wanted to start this by showing you a small animation of how we think the structures form in the universe. Yeah, I'm not sure how visible this will be, but anyhow, so what we think that about structure formation is that the small mass objects, which we call the dark matter halos, are the first objects that are assembled very early in the universe, and from these small mass halos, larger and larger structures form as a function of cosmic time. And in essence, this process is called hierarchical structure formation scenario. So how these larger objects form, so you can see this is a large chunk of the universe, and it represents essentially the cosmic web as best as we know it. So there are all the dark matter halos, and the different structures are encoded in these pinkish colors, and they are formed at the intersection of the cosmic filaments where the matter is flowing towards these halos, and between the filaments there are these vast regions of very low density. This is what we call the voids. And all these structures represent a complex cosmic web that we are trying to understand in cosmological simulations. So we are trying to understand the matter flow from the voids along the filaments all the way to the intersection of the filaments, which is called nodes, to the dark matter halos, and as well baryons, which are so gas and stars, which are accumulating in the dark matter halos pulled by their gravitational potential. And also, not only that we are interested in gravity, but I will tell you a bit more in detail, we are interested about all sorts of feedback processes which may expel actually gas out of the potential wells of dark matter halos back into the large-scale structures, the intergalactic medium and the cosmic voids. So essentially, the aim of these cosmological simulations is really rather ambitious. So we want to, ideally, to provide an ab initio physical understanding of physical processes on all scales. And as you can understand, this is a very kind of bold statement to make. We are very far away from reaching this regime, but this is essentially our guiding star. This is what we want to achieve in some distant future. So I want to tell you a little bit what are all the physics that we have to care about in order to move towards this goal here. So obviously the first thing we have to think about is the cosmology. So we have to assume something about the cosmological framework within which these cosmological simulations are evolved. And the simplest and most natural approximation to assume here is to assume it is called the lambda CDM model. So a cold dark matter model where the accelerated expansion of the universe at late epochs is dominated by the cosmological constant. That's lambda, stands for that. And now in the brackets for each item that I will be really very briefly discussing, I'm just listing some alternative scenarios that some of the research groups in the world are considering as well, rather than kind of standard ingredients in cosmological simulations. And in case of the cosmology, we may think about warm dark matter cosmological models, or about self-interacting dark matter. We may think about the equation of state for dark energy, which evolves as a function of cosmic time, or about more exotic models where dark matter and dark energy are coupled together as a single entity. So moving next, obviously one of the most fundamental ingredients of this cosmological simulation, and to a first approximation is the main driver of the growth of cosmic structures, is to think about how to include gravity. It turns out that Newtonian approximation for gravitational interactions is really a very good and robust approximation to make in cosmological simulations, essentially on a vast range of scales. So we can just not think about GR in majority of simulations, and this Newtonian approach, of course, we incorporate for dark matter, which is providing most of the mass, therefore most of the gravity comes from there, and also to baryons, so gas and stars. One can think about relativistic corrections if one is simulating such large chunks of the universe that one reaches the horizon scale, or one can think about GR connections if one wants to simulate objects which are very compact and collapse, such as close to the black holes, for example. Of course, there is now a very big interest in modified gravity models, so extensions beyond the Einstein's theory, and these are led by a number of large-scale surveys, such as the Euclid, that want to detect any departures from standard gravity, if possible, from a large sample of galaxy surveys over different redshifts. So once we are done with gravity, next thing we have to think about is baryons, actually the component that we observe in the universe. And for gas, what we usually assume is ideal gas hydrodynamics, so what we all learned, the Euler equations that we learned in the university courses. And for the stars, we assume usually they are fluid, which is collisionless. And these are the standard ingredients, how we deal with that. Again, there is a plethora of very complex physics that one can think to build on top. So one can consider non-ideal gases and include processes such as conduction, viscosity. Obviously, magnetic fields are important on a vast range of scales. One may think about this. And then thinking about the stars, eventually stellar collisions do happen and are very important in modeling on small scales. So there, the collisionless approximation breaks down. And finally, if one thinks about just the star or the stellar envelope or the winds emanating from stars, we have to then think about the hydro effects, because stars are actually very well described as ideal gas spheres. Obviously, I told you a little bit about the gas and about the stars. We have to think about the processes that convert gas into stars. And to be able to do that, gas has to cool to low temperatures. So we have to worry about gas-radiated cooling and heating processes, and also about all different physics that may affect the temperature of gas. And there is an umbrella term which I will talk about extensively in this talk, which we call feedback. So feedback essentially is any injection of mass, energy, momentum, metals into the surrounding medium from different sources, such as stars, such as supermassive black holes, that affect the surroundings in a way that the properties of the object itself is affected in turn. And that's why there is this feedback loop between a given astronomical object and a larger scale environment around it. And we have to worry about this. There are more subtle effects, like the non-equilibrium low temperature cooling, where one cannot use a nice tabulated base for cooling and heating processes, but solve very complex networks of the cooling and chemistry rates. One has to obviously, thinking about comparing with observations, has to worry about the dust, and this is giving us one of the major headaches in this field, turbulence, structure of giant molecular clouds, and so on and so forth. And finally, I would just like to mention that there is a very important process that happens in the early universe. We don't know exactly when it starts and when it ends, but roughly between redshifts of 8 to 6. And this is the reionization of the universe. And usually this is done in the form of just spatially uniform but time-varying background, because for the coding purposes this is the simplest way to go forward. Obviously we know that reionization is very patchy, so that there are many different sources that have different ionizing emissivities, and one can try to do either a simple accounting for these local sources, such as the mini quasars, or galaxies themselves, or one can do the cool, sorry I'm blocking part of the slides, but otherwise I'm invisible, so you have to bear with one of these compromises. There are also the really exact methods, and this is to do the full radiated transfer on the fly while the cosmological simulation is running. And actually there are a couple of groups that have done this just recently over the last couple of years, so there is a really breakthrough in this field. But I won't spend more words about it in this talk. So now, having told you about all this complex physics, which ideally we want to include in cosmological simulations, I am going to take a step back and tell you a little bit what was the state of the art when we included only gravity. And this is what is called the pure dark matter only simulations in lambda CDM cosmology. So as I told you, to a first approximation, gravity is really a driver of structure formation in our universe, and it's something that we understand very well, and we know very well how to discretize in the codes and obtain very accurate calculations of gravitational interactions between a set of particles. Essentially, that's what we are doing. So I just want to tell you about the progress in this field, which was really quite astonishing. So from the very first work by Peebles in the 1970s, this is how first kind of cosmological simulation looked like. And this is 40 years later, the state of the art where we are nowadays. And this plot is telling you something about this progress. So it's telling you the simulation number number of particles used in a given simulation as a function of the year of the publication of the paper. So you can see this a remarkable rise in the computing power and in the accuracy and dynamical range of dark matter only simulations. And this last example here that was done in 2012 is actually beyond the plot. So this is really quite actually amazing, the progress that has been made, and these simulations have been instrumental in understanding the distribution of matter on large scales and also interpreting from galaxy surveys what is the distribution of matter on large scales. However, I think we are past this point nowadays because we have to worry much more about the baryons. And there are many different reasons why we have to do that. Well, one, the most obvious one, obviously baryons, gas and stars, these are direct observables, unlike the dark matter distribution. So if we want to make comparison and predictions for observations, we must model the baryons to be able to do these predictions accurately. And for example, I'm giving you just two ideas here. If you want to make predictions for the most distant snapshots, how the galaxy look like in the distant universe, which Hubble ultraviolet field is, for example, providing, or if you want to study the large diversity and morphologies of the galaxies in the local universe, all these processes need to be understood, including the baryonic physics, rather than just gravity. And also, importantly, there is another issue, and that is related with cosmology. So these simulations are progressively used as a very good tools to calibrate our knowledge about the cosmological parameters to tell us more about the universe we live in. And it is now well established that the baryons interact with the dark matter distribution and may affect our inferences of cosmological parameters through the redistribution of dark matter. So for example, dark matter may be more compressed because of the effect of baryons that pull the gravitational well deeper in the center of some object, or it can be distributed on much larger scales. This is of course important, for example, for the weak lensing surveys, and there is a recent example from the DES data which is very exciting for cosmology. So if we want to understand cosmology and not only astrophysics, we have to understand what baryons are doing in cosmological simulations and also hopefully in the real universe. So what is the problem here? Unfortunately, in a simple way to say this, there is not a well-defined minimum spatial or mass cutoff scales that we know that we have to simulate up to. So there are a bunch of processes, very complex nonlinear processes, that occur on a vast range of scales. And in this slide I want to a little bit tell you about this. So essentially, if we want to understand something about statistical sample of the galaxies or about the cosmology, we need to simulate a relatively large chunk of the universe, and this would be of the order of 10 to the 9 parsecs. So this is our kind of our simulation box, how large it should be. Then we want to understand actually the galaxies that form within these simulations, how they look like, and typical scales of galaxies are under 10 to the 3rd parsec. So you can see a huge jump in spatial scales that we have to achieve here, but this is where the whole story just begins, because afterwards, to know the luminosity of a given galaxy, we have to understand the star formation rates, star formation efficiencies, and this is all regulated within the giant molecular clouds, where the typical time scales and spatial scales are very small, so the spatial scales go from 10 to 100 parsecs. But then we know that the efficiency of star formation in giant molecular clouds is also largely affected, actually crucially, by the supernovae events. So massive stars explode as supernovae and release really huge amounts of energy into the surrounding mediums. So if we want to understand the supernova remnants, we have to think about the scales of 0.1 parsec. And then, if you want to think about the effects from massive stars, the mass loss from massive stars, like the Moltke stars, for example, then we have to go to prohibitively small scales of 10 to the minus 8 to 10 to the minus 6 parsecs, And ultimately, I won't make a much argument in this talk, but we know that supermassive black holes are really energetically very important in regulating perhaps the entire properties of galaxies and even on larger scales. But if you want to understand the accretion processes onto a black holes, we have to think about the scales below 10 to minus 6 parsecs. So you can see this range, dynamical range, is nothing that we can breach nowadays in computer simulations. This is completely beyond what we can do. So it will take many years to cover all these scales. But there is a second problem. Even if we had some super fancy code and ultimate machine where we could cover all these scales, we still couldn't solve the problem. And the reason for this is that we don't know the physics ab initio in many of these different scales, so we just don't know actually how to solve these problems from the first principle, so we have to make some assumptions. And these some assumptions, in very crude terms, they are called the subgrid models. So essentially we are modeling all the effects that we know of with a set of well-defined equations, but on the scales where we start to either not resolve the physics or we don't quite understand it in detail, we adopt something that is usually called the effective models. And these effective models are some simple parameterizations of physics, and they usually have either free or tunable parameters. And these free or tunable parameters are then constrained with observations. So we do a realization of a patch of the universe, and we have these free parameters that we have to somehow choose their values such as that we obtain some observables that make sense. And that's where actually the devil lies, in this little detail here. So before I enter into the details, where is the problem, I just want to tell you the state of the art in the current field of cosmological hydrodynamical simulations, which are trying to incorporate as much of physics as currently possible. So we had a little breakthrough a couple of years ago, 2015 roughly, where several independent groups have managed to reproduce large-scale cosmological simulations with sufficiently large dynamical range to, for the first time, study statistical samples of galaxies with properties of galaxies resolved as well in these simulations. So there was, I'm just listing here a couple of projects and flashing their names. There was the Eagle project, led by the group in Leiden and Durham. There was the Horizon AGN project, led by the group in Oxford and in Paris. There was a Magneticum project, led by the group in Munich. And there was a Massive Black 2 simulation led by the group in the US in Pittsburgh. And finally there was Illustris, and Illustris the next generation, and these are the projects I was involved with. So I will just spend a couple of words speaking about this particular project. So essentially what was the main kind of breakthrough in these simulations, and the other groups have really achieved similar levels of breakthrough, which gave us really confidence that we managed to understand something, because all groups have used different codes, have used different implementations of physics and so on. Regardless of that, what we have obtained, and this is really one of the major stepping stones in this field, we have managed to obtain the morphological diversity of galaxies in the local universe. So essentially we have reproduced the Hubble tuning fork diagram, and that was for the first time that we have managed to obtain that. So we managed in a single simulation to represent the galaxies that look something like elliptical galaxies, and then we have managed to present a fraction of galaxies that look like spirals, with or without the bars, and a fraction of galaxies that look like irregulars. And before these simulations, this really hasn't been possible to do in the past. So simulations would either systematically produce only elliptical galaxies or only these galaxies, to say it very roughly. And even some people questioned our cosmological underlying model, the lambda CDM, for the failure to reproduce galaxy morphology. Now we know that this has to do nothing with the cosmology, it just had to do with inaccuracy of numerical methods and two coarse physics that we have been using in the past. So I want to tell you now a couple of words about why we think this morphological diversity comes about. This is a rather busy plot, so I won't spend too many words explaining it really in detail, but I will just give you a flavor of what I'm trying to tell you here. So on the y-axis, I'm showing you the black hole mass, which is plotted as a function of the stellar mass of the host galaxy. And we know this is the so-called black hole scaling relations. We know observationally, so all these black points and observational relationship, that there is a link between two. And this is one of the arguments that has been advocated, that black holes are influencing the galaxies, is exactly this relationship between the two. So this color histogram is what we get from our simulations, from Illustris, and you can see that there is a good match to observations, but more importantly than that, there are some very interesting features to note here. So this color histogram has been colored according to the G-R colors of galaxies. So here are blue star-forming galaxies on the bottom left, and on the top right there are red and dead galaxies with quench star formation rates. And as you move along this sequence, you can actually go back now in your parent simulation and look, oh, what are the morphologies now of these galaxies? And indeed, when you look here, you find mostly these galaxies, these dominated systems with small bulge components. As you move along these relations upwards, you find some galaxies that have a dominant bulge component. And finally, at the tip relation, there are the elliptical galaxies are sitting there. And then if you look at this morphological or color transformation and you relate it with the black hole mass, essentially what you find that for a given galaxy, so you can fix the stellar mass, there is some critical black hole mass above which the galaxy color or morphology is changed, and this is what we say, this is changed because of the supermassive black hole feedback that is acting on the galaxy. Large amounts of energy are coupled to the galaxy and lead to its morphological transformation. And so this is looking rather exciting, and we were very pleased to get these results. And you can actually kind of verify this. You can run the same simulation and completely switch off any feedback from supermassive black holes, and you wouldn't get this sequence. You wouldn't get massive red and dead galaxies and the tip of this relation at all. So having told you this, now I want to start the second bit of my title, the critical bit, and tell you why I think what I told you so far is actually very rough picture, and we have to do much better to understand what's happening. So I'm showing you now here one of the fundamental plots that one can make in this field, and this is the stellar mass function. So it's actually telling you the frequencies of galaxies living in a given bin of the stellar mass. The observations are these great symbols, different lines. The pink ones are from the work of a student of mine, Nick Hendon, from one cosmological box, a more recent incarnation of physics. And these different gray lines, I hope you can see them a little bit, are from this EAGLE project and the Illustris project I was involved with. And you can see, to kind of first approximations, all these different lines are matching observations reasonably well. So we would say these stellar masses look reasonable in this observation. There is no perfect match, of course, but it's not completely off. But then one can start to be slightly more critical and say, okay, but all these simulations have actually used these different subgrid models for incorporating physics that we don't know very well in these simulations, and then they have achieved very similar results. Isn't this worrying? So what does this tell us actually about the predictive power of the simulations if we use different models and get the same result? Whether there is some fine-tuning of these free or ill-constrained results that we don't know, and that we need are we actually doing physics, or we are just fine-tuning to observations? And what is the purpose of the simulations, and how can we improve these simulations to actually learn something about the physics? So these are really the big questions that are motivating nowadays the community to move forward. So until this point I have spent too much time, so I'm going to go even faster now, and I will just tell you a little bit of some efforts that my group was doing recently in trying to go beyond the current state of the art. So one way that we think is really important is to resolve the small-scale physics processes in the vicinity of supermassive black holes, given that we think they are such important ingredient in regulating galaxy colors and morphologies. This is the work by my former student, Mike Curtis. So what he has done here, he has simulated and isolated this galaxy. This is always the same galaxy in the top row. And then he has developed a model where one can refine spatial region in the vicinity of supermassive black holes to much higher and higher and higher resolution. And this is something that we call super Lagrangian refinement method. So here is the underlying computational domain, which is a Voronoi mesh. This would be a standard simulation, and this would be a simulation with this special refinement around the supermassive black hole in the center of this panel. We can zoom in further and further, so you can see there is a huge difference in spatial scales that we now can probe with this type of simulations. And now, what is the interesting bit? Well, actually, we can now put exactly the same simple physics of feedback, just like thermally dumping energy into the surrounding medium, with our standard simulation and with the simulation where we can cranked up the spatial resolution by more than a factor of 10 in order of magnitude. And what you can find here is a very striking difference. So this is exactly the same physics. There is nothing changed in the physics. Here what we find is essentially we dump large amount of energy, the gas in the center becomes very dilute, becomes very hot, this is the temperature map, and essentially there is a spherical blast wave that propagates from the center of the galaxy, and that's how morphological transformation of the galaxy happens. However, in this simulation, given that we are resolving much finer spatial scales, we are essentially managing to resolve the inner bit of the galactic disk, which has very high densities and also high pressures, and these high pressures actually confine this outflow, and it becomes a bipolar outflow that flows out of the poles of the galaxy and leaves essentially the rest of the disk of the galaxy completely unchanged. So we are finding a very different picture here, and we just changed the resolution. One can do similar type of games not only for supermassive black holes, but if one wants to understand the interface between the supernovae and the surrounding galaxy. This is an example from a recent paper of my student Matthew Smith. So essentially he has modeled a supernovae exploding in a galactic disk, and this is what happens, how the disk, just focus on these blue panels, these are the gas density maps, how it looks like when you increase the resolution from 2000 solar masses all the way to 20 solar masses. In one case you are getting very clumpy disk, and in one case you get a very smooth disk. So the morphology of disk is changed just depending on the resolution that we can achieve in simulations. And of course this is a boring aspect that we have to understand in detail, and we are actively working on that. So going back to our example of supermassive black holes, we can actually run these simulations with super Lagrangian refinement in full cosmological framework. And one of the interesting objects that we want to understand is actually how the first quasars come about, so how these supermassive black holes can grow to such enormous masses. We think about 10 to the 9 solar masses by redshift of 6. And this is the work of Mike Curtis again in MNR's letter from 2016. So we have simulated such a cosmological simulation of a quasar forming, and what we find here, so this is a cosmic web, the filaments that are bringing gas to the center. There is a massive outflow coming from the quasar, but we can zoom in all the way to the central galaxy. In the blue, you can see there is a galaxy that looks pretty much like a disk, and there is again a bipolar outflow coming out of the galaxy. You can look at the kinematics. This is the projected velocity. So again, you find largely rotationally supported system that has a massive black hole with a massive outburst. So no morphological transformation whatsoever. So I think here we have to rethink our theoretical ideas, how morphological transformation and the Hubble diagram comes about. So moving on, we can think about different ways how we can test physics. Rather than just changing the resolution, we can actually change the physics that we put in our codes, where we have uncertainties whether one physical model is correct versus the other. And a simple way to do that is, for example, in case of supermassive black holes, we can think that the outflow coming from it is either energy-driven or it's radiation pressure-driven. And currently there is no consensus on this. So this is from the work of my postdoc, Tiago Costa in Leiden, and here are some, just focusing on these two top panels from the brevity of the talk. So there is an outflow coming from supermassive black holes in this energy-driven scenario, and you can see a very massive hot outflow, and here is an outflow coming if we do a full radiation transfer simulation on the fly together with hydro, and the outflow properties are quite different, so the temperature difference here is more than 1 order of magnitude, and we also find there are significant differences in the morphology of the galaxy itself. Okay, so in the last couple of minutes, to be precise, I'll tell you a little bit about the AGN jet feedback. This is another very interesting field on its own, and it has been a lot of interest coming from it because of the Hitomi observations of the Perseus cluster. So this is a little bit of a joke on me. In the past, rather than being able to resolve the AGN jets in cosmological simulations, we would just identify two spheres and dump some thermal energy to mimic what the radial lobes are doing, so we were doing this by hand. But nowadays, what we are trying to do together with my postdoc Martin Byrne is try to devise a very well numerical posed method to resolve hydrodynamical jets up to large scale. So this would look like if you would fail to resolve the relevant spatial scales, you would have no jet. And in a simulation where you actually have extremely high resolution in the whole jet region, you can see a large jet coming from the center of the galaxy. Actually, these dynamical jets can propagate up to 200 kiloparsec across, and we can simulate that all in a galaxy cluster that is up to 1 megaparsec in a virial radius. And what is interesting here is not just to look at the temperature and density of the jet, these are the most obvious things, but actually to look at the velocity structure and the vorticity to learn something about the turbulence that can be driven into the intercluster medium. And this is exactly what Hitomi has tried to observe before it, unfortunately, the satellite failed. So what we have done here, we have tried to understand how much of jet motion, so the turbulent eddies that develop at the edge of the jet, can be propagated into the cluster medium and provide some heating source. It has been widely advocated in the past literature, and how much that can match the Hitomi observations. The bottom line is really simple. These are the simulations with the jet only, and if you look at line of sight velocity, you have no significant velocity field coming out of that. So essentially, the whole velocity is along the jet itself, and there is no propagation of the velocity field further away from the jet cocoon. However, if you include a realistic substructure motion, so galaxies within a galaxy cluster, this is just like depicted in this simulation snapshot here, then you can get velocities, and this is at the Hitomi resolution, that actually match Hitomi observations very well. So what is that telling us is just the bulk motions due to the satellites orbiting in a galaxy clusters are completely consistent with Hitomi observations. There is no evidence that the turbulence is significant driver of any heating or pressure support in the course of galaxy clusters. So am I out of time?
No, it's okay. I'll give you my 5 minutes. So.
Okay, last slide, I promise. So I just wanted to briefly flash about one other exciting topic, and this is to think about the black hole spins. So we all know from the no-here theorem, the black holes are characterized by mass and the spin and by charge. For astrophysical black holes, we don't care about the charge, so we care about the two things. Spins are extremely hard to model, because there is a small-scale physics which is rather complex, and then usually cosmological simulations have just neglected the spins. We are trying now to do that. Davide Fiacconi, my postdoc, is leading this effort, and essentially what he has done, he has interfaced our hydro calculation on large scales with an analytical model for the Shakura-Sunayev, so a geometrically thin, optically thick disk, that is attached to the black hole particle itself in the simulation, and he can then self-consistently calculate the mass flow onto the disk and the angular momentum flow, and then he can look how the actual angular momentum of this disk changes as a function of larger scale angular momentum that we can resolve in the simulation, and ultimately how the spin of the black hole changes. So why do you think this is important? Well, you all know about, we are entering this realm of gravitational wave astronomy. We are really excited about the new results and the recent detection of the neutron-star mergers, and to understand actually the collapse and the merger of these objects, spin is one of the fundamental properties that is going to regulate the merger itself and the gravitational waves that are emitted out of it. So we really, to catch up with observations now from advanced LIGO and Virgo, we need to move into this field. And here is just a little representation what this looks like. So this is a very turbulent cloud. The turbulence is driven on large scales. And the gas, there are some compressive and some solenoidal modes. Compressive modes are funneling the gas to the center. You can see the zoom in over in the central region. So this is the black hole particle, which is just gravitationally interacting with the rest. And this accretion model, the Shakura-Sunayev disk is attached to this black hole particle, and once we calculate all this accretion rate and angular momentum onto the disk, and we include the Butler-Peterson effect, we can then look at a very interesting quantity, and this is the scalar product of the spin of the black hole with the accretion disk. And what that tells you, if it's 1, it's aligned. If it's -1, it's contra-aligned. And you can see these are different runs, and the curves keep flipping. And this is very exciting because we think we are in this picture of chaotic accretion, where the black hole spin can change its orientation depending on the angular momentum of content of gas from large scales, how it is delivered to it. And that obviously is going to change the radiative efficiency of the black hole and the accretion rate. But now I really have to stop, and I will just come to my conclusions and tell you that we really have to worry quite a bit how to accurately calibrate galaxy formation simulations to extract more physics and less tunable free parameters. I think the next generation subgrid models are very encouraging. I think we are moving in the right direction to understand the physics of star formation and black hole accretion and feedback in more detail. Obviously, the spatial resolution requirements are very daunting, and we have to talk with the small-scale community doing these processes, but I think the future is bright to tackle these processes. Thanks very much.
Okay.
Okay. Debora, thank you for a very nice talk and very informative for me especially. And one question, what is the reason to change the speed of that hole?
Yes. So the spin changes due to the two distinct reasons. So one reason is when there is a gas accretion, the angular momentum of the disk around the black hole will change, and that ultimately this gas will propagate, so it will lose some of the momentum, will come closer to the black hole, and that might change the spin itself, and that's radiative efficiency. There is a second reason, is that the disk may warp, and this is really to the Butler-Peterson effect, and this warp will exert a torque onto the black hole spin, and that can change its orientation.
It's interesting.
Yeah. Please.
Okay, Debora, thank you very much for this very, very spectacular, let's say so, presentation. But I wanted to ask you something because a few years ago, it was, as I understood, you used just Newtonian gravity plus dark matter as your starting point in your simulation.
Yes, that's correct.
And a few years ago, it was shown that this model completely fails to explain baryonic Tal-efficient relation of gas-rich galaxies, for which mass is very precisely.
Yes.
You know McGaugh and these
Yes.
Mont people.
Yes.
And is there some in the
There has
meantime
been
advance in
Yes.
progress?
Yes, there
And
has
another
been.
question related to this. This year, a few months ago, I think Gensel or other people observed rotation curves in galaxies which are at redshift 2. It is a peak of galaxy formation, and these rotation curves are completely Newtonian, indicating that there is no dark matter which is essential for forming galaxy. As I understood, first dark matter halo is formed, and in the center then baryons form the galaxy. So is there some advance in the meantime in explaining these disagreements with
These groups, yes. So I would say, first statement to say there is no fundamental disagreement that we think that exists. So I don't think there is any strong evidence that calls into question departure from the lambda CDM model. If there were, we would be really excited because we would learn something fundamental about gravity or about the cosmological model. Unfortunately, all these claimed disagreements are rather marginal. So there are some assumptions that are made, and given these assumptions, there are some tentative disagreements. So regarding the baryonic Tal-efficient relations, actually the most recent works of my group and other groups like the FIRE projects from Caltech by Phil Hopkins actually have found reasonable agreements with the baryonic Tal-efficient relations. Again, these agreements are not perfect. We are not perfectly reproducing the observations, but there is no evidence. There is so much, as I try to say here, uncertainty in modeling the baryonic physics that we think we have enough space for account for that rather than change some fundamental properties. Same holds for the high redshift galaxies that Gensel has been discussing. So there are other issues as well, as you are certainly familiar with. This is called the small-scale crisis, the problems of too big to fail satellites, the small mass satellites that are we produce in too high numbers with respect to what observations of the local group are telling us. But these are, again, all really marginal, really pushing the tension that exists. So we would be excited if we were convinced. that there is a real tension here. So far, I wouldn't claim that there is a
Because I
real...
read some discussion on Nature blog, Nature magazine, which they try to modify the essence of dark matter. So
Yes.
to introduce some interaction, they calculate some...
Self-interacting dark matter, yes. So this is a much more, I would say, promising model than MOND. I think MOND is a little bit reaching its dead end. Self-interacting dark matter models are rather exciting. I think they are not ruled out at all. They are more exciting, I would say, than even warm dark matter models, because warm dark matter models is known they have very difficulties on large scales, on density profiles of galaxy clusters. They have big issues there. Where self-interacting dark matters with a cross-section for interactions that depends on the velocity actually naturally solve this problem, because they behave just like lambda CDM for large objects, but they have departures of small objects. They are not ruled out, and there are many people working on that, but again, there is no firm evidence that they are needed.
And just one, I'll restrain myself to one question / comment. When you showed the stellar mass function,
Yes.
and when you implied that they are pretty similar, considering that the total mass function, or I think even stellar mass function, is pretty robust method of implementation, you can see from that line, considering the papers of Zarya Lukic and Ketin Heitman, so basically all the mass function, all the different mass functions, including the first sector, look pretty similar, considering that they are spanning a lot of orders of magnitude.
Yeah, no, of course you're right. So you have to be very careful when you interpret these plots, because they are on the log scales and there are many orders of magnitude, so you tend to hide the differences.
Yes.
But you can do, I just showed it for illustrative purposes, you can look at many different quantities, and you can find, obviously some of these simulations disagree in some properties, but they agree in others. But this agreement, it's a little bit worrying, because the physics is different that has been assumed. So is this just a coincidence? Is this some parameters that we have used actually shouldn't have these values? Is there some physical processes we have invoked maybe shouldn't have that form? So this is what I have been trying
By
to
the way,
say.
if you haven't, I did a couple of things with the mass functions as well. So one of the things where differences become pretty obvious is on the very high redshifts.
Yes.
So basically there you can really, even in the log scales, you have distinct separation between the different...
Yes, indeed, for this simulation sets that I have shown you, there are differences at high redshifts, and I think I mentioned that in my concluding slides. So by observing more objects at higher redshift, obviously they become bigger, so you have to worry how much you can constrain your models. But many of the constraints will come from higher redshifts, and that's why WST is so exciting, because it will tell us something about luminosity function at very high redshifts. Possibly will tell us something about also AGN luminosity function at high redshifts that can constrain the formation mechanisms of black holes and their energetics. So definitely.
Thank you very much.